And today we're doing correlation and linear regression. Okay, so let's take a look at this scatter graph. And well, if you look at the way the data is distributed, it looks like a line could fit through this. Like you could draw a line of best fit to model the relationship. So it looks like a linear relationship. So when there's a good linear relationship, like above, we say there's a strong linear correlation, okay? A strong positive, I should say. Because the slope of that line you would draw has a positive slope, so we say a strong positive linear correlation. Okay, now if it's positive, that means as one increases, the other increases. As height increases, the weight in general increases. Okay, when one quantity increases and the other decreases, we have a negative correlation. Okay, and if the scatter graph is all over the place, then there's no correlation. Okay, so let's take a look at an example of a line of best fit. And here we have some data. So I'm going to type that data in to my calculator, into C1 and C2, and then go to symbol and make sure everything's okay. We've got C1 and C2 there. It says linear, there's a check mark, there's an equation there, it looks all good. So now if I go back to two variable statistics and click on stats, then we have an R value, which we'll talk about in a second, and over here we have statistics on X and Y. This is where you can find the mean of the X and the Y. So if you want to find the mean mathematics score and the mean biology result, then you can get it in here. So the mean mathematical score is 32.75. That's exact, actually, 32.75. And the Y, or the biology scores, it is 23.75. 25.375, sorry. Okay, next says plot and label the mean point. Now the point is the line of best fit should go through the mean point. So let's go down here to X value 32.75. That's this is going up by 2, so 32.75 is about here, and the Y value is 25 point something, so it's probably right about here. Okay, label it means write down the coordinates, 32.75, comma 25.375. So that's the mean point. And whenever you draw a line of best fit, it should go through there. Okay, you want to draw a line of best fit so that it fits the points well. And you should, a good rule of thumb is to have approximately half the points above and half the points below the line. So I'm going to try to draw it freehand. You can do it a lot better with a ruler, but something like that. Okay, so that's the line of best fit, and it says predict the biology test score for someone who scored 40 in math. Well, you can just use your line. You can get the equation of the line too, but you can use the line and approximate this way. So right in the middle over here is 29, so that would be 29. Okay. Explain why it would not be sensible to use your line to predict a biology score of a student who scored 11 on math. Well, if you look at 11 on math, it's way over here. It's called extrapolation. It's outside the range of the data. Outside the range of the data. So it's not reliable. Because we don't know if that linear trend continues. It could be curvy on either end. Okay, next let's look at what your calculator can do to show you whether or not there is a positive or negative linear correlation. Your calculator can spit out a statistic for that. It's called Pearson's product moment correlation coefficient. Okay, if we're close to 1 or -1, there's a strong correlation. So for example, in this diagram in D, looks close, very close to a line, so the correlation coefficient is going to be very close to 1. It's probably about 0.95 or something. So, and we look in part A, we have a probably moderate to strong negative, because the slope is negative if you draw a line, strong negative linear correlation. And in B and C, they're kind of scattered all over the place. I wouldn't draw a line through them at all. I would say no correlation. They seem to not be related at all. Down here, like I said, very strong maybe? Very strong, positive correlation. And here I would say strong and positive because the slope is positive. And I should have said linear here, by the way. Oops, linear. I always say linear when it's a linear correlation. Strong, positive, linear correlation. Okay, we can actually calculate the R value, which tells you how strong the correlation is. Using our calculator, let's go down to an example. And this is a good rule of thumb. Over 0.75, we would say strong. 0.5 to 0.75 moderate, and weak between 0.25 and 0.5. Although depending on the source, this is kind of an opinion. So depending on the source, you might get different values. Okay, so let's get the correlation coefficient, or R, from this data here. And let's go back to the app and clear all. And type that in, 5.6. The most common mistake in these statistics questions is typing in a number wrong. So make sure you got the correct data values typed in. Okay, it looks all good. Always check symbol. In symbol, we got C1, C2, we got linear. You need linear, and there's an equation popping up there. It looks good. Sometimes you got to click plot. Nothing comes up here. Sometimes you got to click plot. Go back again, and oh yeah, okay, make sure you always do that, because that equation that was there, it was an old equation. You have to click plot for the data values to be entered into the calculator, and it spits out an equation. Anyway, let's go to apps. Now here we're back to where the data is, and you click stats, and there's the R value. Most of this other stuff we don't need, but the R is about 0.96. So that's a very strong positive correlation. Very strong, positive, linear correlation. Okay, now you should always look at the picture. So let's go back and look at that picture. Let's go to plot. So the data does look linear. Actually, if you want to see it better, you can go to Menu, Zoom, then go to Auto Scale, and you can see all the points. So this does look like it fits the points well. But you can't just look at the R value, because we have, over in this situation here, all of these data values have the same correlation coefficient. But obviously some of them are not linear or non-linear. So you would not do linear regression on these. That doesn't make any sense. This one, yes, looks linear. This one has an outlier, so it does look linear. I might consider leaving the outlier out, because it looks like the points go like this, but it depends on the real life situation. So always look at the picture to make sure there is a linear relationship before you calculate the linear correlation coefficient. It's important to note that correlation, just because they're correlated, doesn't imply causation, okay? So if the two things are related, it doesn't mean that one causes the other. So you have to be careful about that. Regression. Okay, so this is, before we drew a line of best fit through the mean point and we just kind of eyeballed it, regression will always give you a computer generated equation of the line that minimizes the squares of the residuals. The residuals are these distances here, these vertical distances between the points and the curve, and it minimizes the square of those distances, okay? So the regression line is an algorithm that spits out an equation that matches these points as much as possible vertically. Okay, we call that the y on x regression line. Okay, this is just the x is the independent, the x is the independent, the y is the dependent variable. And we call it the y on x regression line. Okay, so we have the form y equals mx plus b basically. So we're going to get the equation. We actually already have this data in our calculator. And under symbol, as long as you get on linear, it gives you the equation. So the equation is y equals 2.93 x minus 3.86. Okay, then we can use that to make predictions. Here we just substitute in 6.8. Here we also substitute in 4. Okay, to make these predictions. And on your calculator, you can actually copy this whole equation. So you can use all the digits to get a more accurate answer. So press Shift and then copy. Let's escape and press paste. So then you can replace the x value with the actual number, which is 6.8. And we have 16.1. And you can do the same thing. You can copy and paste this again. Change that to a 4. 7.86. Now this is not recommended actually, because the y and x regression line is best for predicting y values when you have an x value. So this is not going to be a reliable prediction. Okay, but we can try it anyways. Okay, we can solve for x just by doing 17 plus 3.86 and then dividing by 2.93, and that gives you a value of 7.12 to 3 significant figures. Okay, now sometimes, well, actually the a value, the slope, always has some sort of meaning. So if x is the average number of hours of sunshine, y is the number of visitors, so the slope, or a, represents the increase in the number of visitors per extra hour of sunlight, for instance. Okay, so more sunlight, the more visitors we have. Okay, b in this case, well, sometimes it doesn't mean anything. So it usually means initial value, but the b is negative 3.86, so you cannot have a negative number of visitors, so no real meaning. There's no real meaning here. That happens sometimes. Sometimes this has a meaning, like an initial value. Sometimes it does not. Okay, let's look at the next question. And let's go and type this onto your calculator. So let's clear it and then type in the data. So I've got all the data typed in, and we want to see what the graph looks like. So let's go to symbol, make sure everything's okay. We got C1, C2, linear, click plot, and it does look like it is a linear relationship. If you don't see that, you can go to zoom, auto scale, and it usually gives you a nice picture. Okay, so it does, yes, it looks linear. So regression is appropriate. Yes, it looks linear. Find the regression line, n on t. That means n is a function of t. Well, n is basically our y value, and t is our x value. So n equals, let's go back to symbol, and this is the equation. So 8.05t minus 24.7. Interpret the gradient. Okay, so the gradient is always a rate of change, and it's rate of change of the y value over the x value. So in this case, the number of water bottles sold per day, right? Per 1 degree increase in temperature, because capital T is temperature. Okay, so the number of water bottles sold. Oop, spelled water wrong. The number of water bottles sold increases by 8 for each 1 degree Celsius rise in temperature. Okay, use your regression equation to predict the number of water bottles sold at a temperature of that. That's just doing n equals 8.05 times 19.5 minus 24.7, which we can get on our calculator. We can copy this number again. Shift, copy. Oops, that didn't work. Let me try that again. Shift, copy. You should get this little symbol. We can paste it back here in the main menu and replace the x with 19.5. We get 132. State why it would not be appropriate to use a regression line to estimate the number of bottles sold when t equals 10. When we look at the data, the temperatures are all between like 18 and 22 or 21. So it's way outside the range of data. So not appropriate because it's outside the range of the data. Okay, and that's called extrapolation, if you want to use that word. Extrapolation means a prediction outside the range of the data. And for the last part here, the temperature when 132 bottles are sold. So this is the n value, right? So this equation here is only really valid or accurate or reliable when you're predicting n values given t values. Okay. Okay. So predicting t given n is unreliable.